I welcome you all to this course on diffraction and imaging. Okay. Before going any further, I would just like to ask you, what have you understood in the last class? Because let us have a recap of what has been done and then we will proceed from there. So, what did we study in the last class?
The reciprocal lattice.
Reciprocal lattice. Okay, what did you learn in reciprocal lattice? Okay, the relationship between the real space and the reciprocal space. Okay, what is the relationship between the real and the reciprocal space which you have learned? If A, B, C are translation vectors in I will call it as a direct space. Okay. This is all constructed with respect to a primitive lattice, correct? The lattice is considered as a primitive lattice. Then the reciprocal space, this is the relationship which C cross A equals A cross B dot C, correct? Then what is the basis equation from which this was derived? What is the basic equation from which we derived this relationship? Yeah, that is essentially e to the power of I 2 pi k dot r should be equal to 1, correct? Or k dot r should be equal to an integer, correct? This was the basic relationship from which this relationship between the real lattice and the reciprocal lattice has been derived. So, from this relationship what one can make out is that for every vector k in reciprocal space, there are set of vectors in real lattice in different planes which satisfy this condition, right? Like it could be that k1 dot r could be equal to various values 0, 1, 2, 3 like that, any value which it can take, right? Similarly, we can have k2, okay, is another vector in reciprocal space. Similarly, for every vector in reciprocal space, okay, we have a corresponding lot of vectors which satisfy this condition, okay. That means that all the vectors which satisfy this condition r equals b plus n3 into c, okay. This set of vectors are, when they satisfy, all these vectors are perpendicular to this vector k1, correct? That is what this indicates. Then the other expression which we have derived is that the vector in a reciprocal space, okay, if it r star, that can be written as h into a star plus k into b star, right, l into c star. This way we can represent all these vectors, okay. But both the vectors in real lattice as well as the reciprocal lattice are represented in terms of orthonormal coordinate system, right? That is the way we define this vector. Okay. Let us just take an example with respect to a simple cubic lattice. If we take it, that is not simple cubic, FCC lattice, okay. if we take it, how are the lattice translation vectors of the real lattice of the primitive lattice is represented? FCC if we take, okay, it will be, that's a vector A. I will just write it as for the primitive, that is for primitive lattice. J plus K, right? C is equal to 2 into K plus I. This is how the vectors will come now. That's essentially if you take an FCC lattice and these are all the position lattice points are there. So, this one, this vector, these are all the three primitive translation vectors, translation for the primitive lattice of FCC. Okay. When you use this formula and try to find out these vectors, okay, this will turn out to be one, I am just writing it, but you have to cross check it. It will turn out to be 1 by A, one is I plus J minus K, C star will be 1 by A into minus I plus J plus K. This is what the vectors will turn out to be. Okay. No, when you take it, it will just turn out to be this value. Okay. What this A star in the reciprocal lattice, this means, this vector? No, BCC is a structure. What essentially this, because this represents the translation vectors of the reciprocal lattice which we are looking at it for the primitive lattice, right? This will be nothing but 1 by A. Normally, conventionally, how do we represent a vector 1 0 0, right? So, if you write it like this will be 1 on bar, correct? This will be 1 on bar 1, 1 by A. This is how it will turn out to be, correct? Because when we write a vector, okay, or any direction in a lattice as 1 1 0, it actually means, okay, if A is the lattice parameter, this should be A into I plus J. This is what it exactly means, correct? So, essentially using that same logic, this is what essentially it turns out to be. Okay. So, this defines translation vector of the unit cell of the reciprocal lattice. When this is defined, how this will turn out to be? We can mark this one, all these one will be going from here into the next cell in this direction, another will be going into this direction, another possibly will be going into down into the next one. That is how these vectors will turn out to be, and the magnitude is going to be 1 by A of it. So, once we know these basic vectors, all other reciprocal lattice points we can find out by taking a combination of this, correct? Is it not? So, these are all the basic translation vectors. If we take combination of it, we can find out. If you do that, what it will happen? You take A star plus B star, it will be 2 0 0, correct? Similarly, you can take B star plus C star like this if you do, you find that the reciprocal lattice vectors which are there, okay, are 0 2 0 and the other one will turn out to be 0 0 2. Okay. Automatically if you look at it, the structure factor consideration which you look into it is already taken care of. So, you take whatever be the combination of all these vectors, okay, this, and you can choose any value of h, k and l, you substitute this and finally what you are going to get it is that various reciprocal lattice points. So, what I wanted to emphasize at this point is that the reciprocal lattice point which has been constructed using this relation, okay, automatically takes care of the extinction rules if we construct it with respect to the primitive lattice. That is all which has to be done. That is one important point. Is it clear? Okay, 100 will not come in this, because always we have to, when you take that addition, the addition is always taken with respect to integer values only, because h, k and l has to be an integer, correct? Because I had explained earlier about how to construct and all the relationship in detail in the last class. So, using these vectors we can construct a reciprocal lattice. The same thing which we can do it is that what is the geometrical meaning of this vector algebra? What we have done is essentially, if we take any lattice, okay, we can construct the reciprocal lattice also in another way, okay, that geometrical construction. Suppose we take that the lattice itself is a two-dimensional lattice which we are considering it, correct? Okay. You take this as the origin, okay, then this direction, okay, will be 1 0 0, this direction will be 0 1 0, okay. The third direction is perpendicular to the board, and assume that we are keeping the same type of a lattice one on top of each other to generate with a lattice parameter, and here suppose this is A is the lattice translation vector here, and you take this to be the B, okay. So, what is this plane? This plane is nothing but a 1 0 0 plane, right. This plane will be 0 1 0 plane, correct? Is it not? Okay. What is the plane normal to these 1 0 0 planes? It is essentially drawing a, so this is the plane normal, okay. What will be the magnitude of this value? This will be, that is, if this angle is theta, it will be a cos theta, right. That is what this value is going to be, is it not? Similarly, what will be the plane normal to this 0 0 1? It will be essentially in this direction it will be coming, correct. And this plane normal is nothing but, if this is B and this is the vector C, B cross C will be a vector like this, correct. That is, the direction of the vector is the same as the plane normal, okay. Now, what is going to be the magnitude? The magnitude is going to be essentially nothing but inverse of the distance in magnitude, whatever is the value, it is the inverse of that, that is what it will turn out to be, correct. See, this direction is B cross C, correct. This is what this vector represents, correct. When we write A star is nothing but B cross C by A dot B cross C, right. What is A dot B cross C? It is nothing but essentially volume of a unit cell, okay. What is B cross C? Is the area of the plane. Also, geometrically it means it is the area of the plane, right. That is, I can if this is A, B, and if you take it C, okay, is it not? So, if that is the big area of the plane, okay, A dot B cross C, what it says? It's essentially that divided by, if you take the area of the plane, that will be the perpendicular height. What is A cross? The vector, we are taking an inverse of that. So, essentially magnitude wise, it is inverse of the interplanar distance, correct? That is what essentially what we are taking it, okay. So, on this direction, if you mark the inverse of this interplanar distance at some point, okay, then here also we will be marking an inverse of this interplanar distance. The lattice which it generates, okay, that is the reciprocal lattice. So, geometrically this is the way we can construct it, okay. Is this clear? Okay. Suppose we assume that there is a, at this particular position, at the middle of it, there is some lattice point is there, then what will happen? Then there is a plane which comes in between, right? So, the interplanar distance is half of that. So, its inverse is what we will be taking it, okay. This plane will be nothing but a 2, 0, 0 type of a plane, okay. Automatically this is equivalent to taking a primitive lattice. So, this way also geometrically we can construct a reciprocal lattice, okay. Essentially what we have to do it is that with respect to that same origin, okay, find out the vector, okay. Suppose this distance is A and this distance is B, okay. That is the not B, I will write it as this as D 100, okay. This is a 100 plane, the distance between 100 plane, and here this we write it as D010 plane, okay. So, if we take the inverse of it, that inverse, this is going to be larger compared to this one, right. So, when we mark any point, they will be in this ratio, na? So, that will give rise to, suppose this point we take it as here, this is the vector corresponding to A star, the other one the vector may be corresponding to, it will come here as B star, and if we try to do vector addition, we have the unit cell, then we can, by vector addition we can generate all other points and construct the reciprocal lattice, okay. This is a geometrical way, both are equivalent, okay. But the geometrical way for simple lattices it can be done for visualization, but it can become quite complicated, okay, for many lattices, whereas the using vector algebra it is much easier to do, okay. Is this clear? This is the same which I had shown here, taking a triclinic lattice, okay, and I have shown here what is this perpendicular distance, okay. These are all the distance between the planes, okay. The inverse of it, if we take it in these directions and draw that, we will be able to, okay. And another information which comes, if you take that r star dot r, what it will happen? Plus k into n3, right? This should be equal to an integer. Generally you find that in the books, instead of n1, n2, n3, for the vectors we write UVW, right? then you write that formula HU plus KV plus LW equal to N. When the N equals 0, okay, this is what is called as the zone law, right, which you might have studied. And the 0 means that what we are looking at it is in the reciprocal space. The first plane is what we are looking at it, the 0th plane. Okay. When n equals 1, it gives information about the first plane. Okay. Then the second plane, third plane, like that it goes. These are called as higher order Laue zone planes. Okay. Essentially, by looking at these planes, the information which we can get it is, in the diffraction pattern, we can get information about the complete reciprocal lattice, right. So, when a reciprocal lattice is constructed for this one, the 0th order plane is there respect to this one, the next plane is there, the next plane is there for a particular beam direction in which the beam is falling. When we get the diffraction pattern, okay, analyzing the pattern, okay, generally what we get it in a normal diffraction pattern is only 0th order. But if we change the camera constant, which I will come to later explain, okay, we can get information about the higher order Laue zones also. That means that in a single pattern, we can get various reciprocal lattice sections. Information could be we could get it in the diffraction pattern. If we analyze this pattern, then we can construct the complete reciprocal lattice, correct. So, in principle, if we have the full reciprocal unit cell is available, from that we can get construct back the real crystal structure, correct. That is the philosophy behind this. Okay. So, this is essentially what we have looked at it is a geometrical construction. Okay. We have not talked about diffraction at all. Okay. But we said that there is a relationship between diffraction and reciprocal lattice space, correct. This is what we will look at it now. Okay. What do we do in a diffraction experiment normally? What is diffraction? What do you understand about diffraction? Interference of waves which have some phase relationship. Okay. That you might have studied in optical radiation, right? How these waves interfere. Suppose we assume that a sample is kept here, okay. And another thing which is very important is that diffraction is essentially like a group activity, or scattering from more than one point is necessary for this interference phenomena to occur, correct. Suppose we keep a sample here, okay, and an electromagnetic radiation, because electromagnetic radiation can be considered as can be expressed as a wave, okay. We assume that that is coming and on this, okay, and we assume that it is a coherent beam, or we take that this is to be something like a plane wave which is coming, okay. A monochromatic coherent beam is falling onto the sample surface, okay. If it falls on the sample surface, now what is it which will happen?
It will either absorb or
Huh?
it's either absorbed or
What is absorption? What do you mean by absorption?
like the energy electromagnetic wave which whatever the wave carries is transferred to the atoms in the lattice.
Suppose it does not get scattered. Essentially what happens is that if the intensity of the radiation which comes out on the other side is less than that, we say that the beam has been removed. It could be due to a physical absorption or it could be due to scattering. There are many processes which can happen. Finally, there is a reduction in intensity. When a reduction in intensity takes place, we say that an absorption is taking place, but processes could be different. Okay. Let us not bother about it. So, if we take, we assume that this is the direction in which it is traveling. So, direction you take it to be k0. Okay. Coming. Around the sample, you take a sphere of radius, some radius. Suppose I keep a detector, I can move the detector like this everywhere. Okay. I am just only showing a cross section of it. If I move the detector, what will happen? At some particular positions, okay, at each position, if I look at it, the intensity which the detector is seeing it will be different. Okay. Some regions it will reach a maximum, some regions it may be 0, some regions will have some intermediate value. That is what essentially is going to happen, okay, provided the sample is a crystalline material. Okay. When such a phenomena occurs, we say that interference of the beam has taken place. Okay. Any direction which we can take it, in this direction, suppose this I can take it to be k, okay, wave vector, okay, because we are choosing a reciprocal space to represent it, because we are using a wave, okay, the incident wave, this is the direction in which it is coming, okay, this is the scattered wave, correct, is it not? Okay. Do you expect this to happen in a sample if we do a diffraction? That is, you allow the beam to fall on the sample's surface, the sample, in around 4 pi, okay, at different positions on the surface of the sphere, there will be intensity maxima or minima. So, essentially 2d sin theta equals n lambda. So, if this condition is being satisfied, okay, and there are many methods in which this experiment is being carried out. Okay. Normally in the diffractometer, you move the detector and also the source, that is why we collect peaks at one particular point, but it is always possible that when the beam is coming in one direction and falling onto a sample, there are many directions in which you will be observing diffraction spots. It is not at one position. Okay. That is what essentially is being shown in this particular slide. That is, this is the direction in which the beam is coming. In this lattice, you can have planes like this, you can consider planes in this way, you can consider planes, various directions you can have in the planes. Na? So, whichever planes with respect to the beam direction, it satisfies the Bragg condition, okay, we are able to get some intensity maxima will be taking place. What is the major problem about this Bragg law? The law is very fine, but this equation does not talk anything about discreteness of the atomic lattice. It is a lattice which is, it is telling that between these two planes, if the spacing between the planes, okay, is a particular value, this is the angle theta which it should correspond to, correct, at which the diffraction will take place. But scattering is done by individual atoms, correct? Where are the atoms? That information does not come from this expression, correct? It only tells that between these two planes, that is what it is talking, but not about at what positions the atoms are sitting on the plane, at what point atoms are sitting on the plane, that information is missing from this law. Okay. The basic derivation, if we try to look at it, is that each lattice point is a scattering center. The coherent beam, when it falls onto the sample's surface, it is scattering from each of the point Okay. From each lattice point it is scattering in all the directions. Okay. And this scattered radiation is what we are trying to collect it. Like if I put a detector here, what am I trying to do essentially? In this direction, all the electromagnetic waves which has been scattered from every point on the atom, I am trying to measure it, correct? That is the intensity which is being measured. So, like here if I consider in this particular direction, all the rays which are scattered, because the sample is very small, is large. So, essentially all the rays which are scattered from the various points on the sample, okay, in this direction it is being collected. So, the intensity which we measure is essentially the intensity of the atom scattered in a particular direction from by all the atoms in the sample, correct? That is the information which we are trying to look at it. Okay. We will just try to find out what this value will be in terms of the incident beam radiation. Okay. That is essentially, if you consider an incident beam as a plane wave, okay, this is essentially where the crust which we are showing it. Okay. That means that the separation between them will be there corresponding to wavelength of the radiation, correct? K represents the wave vector, the incident waves, okay, in reciprocal space, and so psi will be A into e to the power of I 2 pi kr. Okay. Here what we have talking about is with respect to this A, we have not defined it, we will not define it what it is. This A can have different values depending upon whether it is an X-ray or whether it is an electron beam, whether it is a neutron to interact. There will be that part of it we will not talk about now, but essentially what is important is that wave nature is described by this phase term only, correct? That is what we will concentrate on. If this wave, okay, encounters an atom, okay, when it encounters an atom, okay, this plane wave is from this point it is scattered in all the directions, correct? This is the incident wave vector k0, okay. This is the, if you put a detector, we are trying to measure the intensity here, okay. Then at any particular point on this circle, because this circle is essentially cross section of a sphere, any point, what will be the intensity of that radiation? The its wave function, the intensity will be, if the intensity here is I0, it will be I0 by 4 pi r squared, correct? That is what the intensity at a distance r from the center. So, amplitude will be, because generally intensity we write as psi star, correct? So, the amplitude will be whatever value by root. So, that is what essentially is being written, that is why 1 by r term comes into what will be the phase factor here. It has travelled from here to here, if it has travelled, e to the power of I 2 pi k into r should be the phase factor, correct, at any point on the surface. So, this describes the wave, okay, which is scattered from by an atom, okay, at any point. Is this clear? Okay. Okay. Now, what we have done it is, the sample contains lot of atoms are there, correct? At a periodic interval they are kept. So, if this is the plane wave which is coming, and if this is the origin, okay, we assume that at that origin, okay, suppose r equals 0, it has got the maximum amplitude. So, we try to write it to be psi is equal to some a, if it ignore, we can write r a equals 1, if you put it, psi will be equal to 1, okay. And then it is being scattered from here, It is by scattered from here in this direction. Okay. So, in this direction by all the atoms, what is going to be the phase with which the scattered wave is coming? That is what we have to look at it. Okay. And at any point r distance where we have kept the detector. So, we will be getting a wave which is scattered from this point, a wave which is scattered from this point, all of them will be joining together. Let us consider just 2 points, this as well as this point. Okay. So, this scattering we call it as an elastic scattering because there is no loss of energy, that is the incident wave, okay, and the scattered wave has got the wavelength is not changed, okay, no energy is lost and it is coherent. So, let us consider this particular case, okay. That is what essentially is being done. So, if it is being scattered from here, okay, at a distance r, what will be its the amplitude, then the function that will be equal to psi into, because though we have to represent it as kr minus omega t, okay, this factor we are ignoring it for the present because that does not, at any instant of time if we consider the time factor we can ignore, only the spatial this one factor we are taking into account. Okay. Then psi will be e to the power of I 2 pi kr divided by that r will be there, correct. That is what essentially it is going to be. Okay. But the incident wave itself, when it reaches here, if it has a psi equals 1, when it reaches here, what it will happen? The incident wave, because some distance it has to travel. Na? What is the distance which it has to travel, that incident wave? That is given by k dot Rmnp. Okay. So, that means that the phase will have this much phase also will be added to the incident wave, right. And then this is what it is going to be essentially is the amplitude which it will have finally of a wave which is scattered from here at a particular point, wave which is scattered from here at a particular point we have. If the scattering, if we consider the beam to be a coherent beam, okay, all the amplitudes will add together, right. The wave functions will add together. If it is an incoherent one, it is only the intensities will add, not the amplitude. Okay. That I will come to later, but now you can take it that it is essentially all the amplitudes add together. Okay. That is essentially what is being done. This is the amplitude of the wave, okay, psi dash is at this particular point. Okay. From this particular point if you consider it, this will be with respect to r dash. From here this is the amplitude. Just if you consider scattering from 2 points in the same direction, this is little bit of mathematical jugglery if you do it. Finally, an expression will turn out to be of this type, e to the power of I 2 pi k r dash into e to the power of k dash minus k will come. Okay. What is k dash minus k? This is incident beam direction, this is k dash, right, and the difference is what is a vector which is going to be, that is represented as delta k. Is this clear? See, what are we trying to do? From this point at this particular direction, we try to find out if I put a detector here, which is very far away, okay, compared to the atomic distances, correct. What is the distance between atoms in a lattice? It is essentially 2 or 3, 0.2 or 0.3 nanometers. Where do we keep the detector and measure it most of the time? It is at 20 centimeters, 30 centimeters, right. So, the distance if you compare it compared to the interatomic distances, it is a very huge distance. Okay. So, from here to here if I take a small another atom position, okay, essentially the beam which comes from here to here also the direction we can take it to be essentially in the same direction. Okay. So, what we are trying to do is that the wave which is scattered from here, what is going to be the, because you can take a sphere find out what it is going to be. From here, the wave when it reaches here, between this and this there is a phase shift has been introduced. Okay, it is a plane wave when it reaches there. Then from this it is at a distance, if this is at r dash, this is at a distance r. Okay. Then again we can find out what will be the amplitude of this. These two amplitudes we add together. Okay. When you add together you get a term which comes like this. Okay. This is essentially what this turns out to be. Okay. This A dash by r, what I have taken it is, that is an amplitude factor which we have not talked about what that, it is to do with the scattering atom as well as with respect to the incident radiation. That part of it we will talk about it later. Okay. So, essentially what is interesting here is that this factor e to the power of I 2 pi delta k dot RMNP. Okay. This is for, with respect to origin, one atom we have considered. In the sample there are in each direction, okay, in one direction m atom atomic points, lattice points are there, another n and another p, then it will be, we have to sum it over all these factors, correct. That is what essentially is written. And in this term, if it depends upon each particular side this factor turns, it has to be within the bracket sigma. If it is independent of the atomic position, then it can be taken out as a common factor. Okay. But what is important is that this is what essentially is important. Suppose what is RMNP? It represents the position of each atom or each lattice point. Okay. So, for each lattice point, this term, if it turns out to be 1, okay, then all these will add together, right, is it not? So, this amplitude of the wave scattered in this particular direction will turn out to be maximum. Then we say that a constructive interference is taking place. Okay. In between points where it is not k is some value k1, if you take it here, for this value k1, okay, suppose all of them do not add together, some of them subtract, intensities will come down, okay, and at some point they could completely vanish, then we say that sum is 0. So, this is what it is. So, the condition for constructive interference essentially is nothing but this delta k dot RMNP should be equal to 1 for each point, correct, is it not? And this is essentially what we have written is the amplitude part of it, correct, of the wave which is coming the detector at a particular direction. And this can be considered in we can write it in an integral form also, right. If you write it as an integral form, then what happens is that this is over a particular volume, we have to consider it. Here what we have done it is, every atom position we have taken and added it, correct. Instead we can integrate it over the full volume also, instead of taking each lattice point. Okay. Then this will be integral dV. Okay. This factor is a factor which depends upon the sample and the primary beam, correct. So, this turns out to be, if it is a X-ray diffraction, okay, this factor will turn out to be the density of electrons. Okay. Otherwise, in the case of electron diffraction, it will be electrostatic potential, how it varies. So, this is characteristic of the sample, okay, because in the sample which we have considered as consisting of, if we represent it like this, each of the point atoms are there. What is it exactly which is happening here? Around each point there is a nuclei, surrounding it which there are electrons are there, okay. That turns out to be some ions, and then in a periodic lattice in between regions also there are electrons are there which are distributed, correct. So, maximum positive charge will come here like this here. So, this density of electrons will be varying it from the core of the nuclei to here. If is the density is going, so density is going to fluctuate, electron density is going to fluctuate, is it not, in the sample. Okay. So that itself is essentially another periodic function. So this is what that n rho represents, nothing but the density and e to the power of this term which turns out to be. This way also we can write it. Okay. So important thing essentially is that delta k dot r should be an integer. Okay. And this we can write it as the same delta k in the last class. What we represented it in another form as a capital K. Okay. That will come to it. This k dot r we write it. R can be written as, okay, n1 into A plus n2 into B plus n3 into C, right. So this will turn out to be n1 into delta k dot A plus n2 into delta k dot B plus n3 into delta k dot C. This is what it will turn out to be. All these things we have looked at it the last class. Okay. What is interesting about it is that this into I into 2 pi into exponential, that is what sigma of it we write it, correct. This how we can write it, e to the power of I 2 pi I h1 into this one, correct, into e to the power of I 2 pi I n2 into delta k dot b. So when each of this exponential term becomes 1, then only it will become, that means that n1 is an integer, then delta k dot A should be an integer, this should be an integer, this should also be an integer independently. Is it clear? Okay. That is what has to happen. When that happens, okay, then the scattering from all the atoms are adding together, they are in phase, correct, and then we will get a maximum intensity. So if the total number of atoms are in any one particular row is m, okay, in each direction maximum value of n, m, n and p equals m, then this maximum value what it can have, this phase factor should be equal to m cubed, it can happen, correct. Okay. This, if you remember, last time we have derived that expression that delta k dot A should be equal to h, okay, all these things which we have derived it, okay. Instead of delta k we wrote it as a k, right, capital K. And we derived that expression that delta k should be h into A star plus all these expressions come. The same derivations follow, which I had mentioned just some time back in the class. Okay. So what is important from this derivation is that every crystal has two important lattices associated with it, the crystal lattice and the reciprocal lattice, right, direct lattice and reciprocal lattice. The diffraction pattern from this what we can make out is that the diffraction pattern is related to the reciprocal lattice, right, and that is one. What is the relationship which happens is that when, because this delta k which we have considered here is between, if this is k0, okay, and if this is the direction which you are scattering k, okay, this is what the vector will be, which is delta k, correct. Is it not? But if this vector turns out to be a reciprocal lattice vector, okay, then constructive interference will take place. because this could have, because this value of k could be any value na, in this sphere what we have considered. We are putting a detector here, measuring it, putting a detector here and trying to measure it. Only at some points, okay, that value turns out to be maximum. For that, delta k will have some special value. That value is that the delta k equals at that time equal to g, the reciprocal lattice vector. And another important factor which you should understand is that the crystal lattice which we have drawn earlier and the reciprocal lattice, the origin for both of them remains the same. If I rotate the crystal, what will happen?
Different
By
waves will be,
the same angle, the reciprocal lattice also will rotate. They are tied together. Real lattice and the reciprocal lattice, okay, the relationship is fixed. So it is as if I take a real lattice and represent it in terms of an orthonormal coordinate system, with the same orthonormal coordinate system, reciprocal lattice is also defined. So if I rotate a real lattice, the reciprocal lattice also has to rotate along with it. It cannot remain separately, right? That's what it's, this factor is very important. Tilt a sample in the holder. What we are essentially doing it is that we are tilting the reciprocal lattice also along with it. So what will be the consequence of it? The reciprocal lattice has got a direct relationship with the diffraction. So the diffraction pattern also will rotate. That's if you put a sample, the beam is coming like this and falling onto it. If I tilt the sample, what it happens? The diffraction spot which has come, when I tilt it, that will also rotate. That means the reciprocal lattice is also rotating along with it. Planes like this, okay. Conventionally you draw like this is what it is, okay. Right? This is D, then you are trying to find out if this angle is theta, this angle is also theta, okay. Then you are trying to find out this is d sin theta, correct? This is also d sin theta. This is how the derivation is done, okay. Suppose you consider a case, it's not, so how do you measure this angle theta? Is with respect to a beam, this is the angle theta. Okay. Is this how we measure angle theta? Okay. Suppose the beam comes like this. Okay. It gets scattered in this direction. Will diffraction take place? Away from this.
Apart from n lambda is 2d sin theta, we should also have periodic scatterer and
No, there is diffraction only. We are talking about no periodic scattering. We are not talking about atoms. We are talking about diffraction from a plane, Bragg law. So what it is that if I take it here, if this angle is theta 1, this angle is theta 2, okay. This is d, correct? D sin theta 1 plus d sin theta 2 should be equal to n lambda. If this condition is satisfied, that's Bragg law actually. A special case is when theta 1 equals theta 2 is a symmetrical condition. That's what you always see in books. This also is given in books, but nobody looks at these pages. This is the most general formula. Okay. Doesn't mean that angle has to be equal for a Bragg diffraction to occur. What is essentially important is that the total path difference has to be a multiple of n lambda. That's what the diffraction condition says. You understand that? That is precisely is the reason when we consider a sample here at the center, when the beam comes in this direction, there are various directions in which where the theta is not the same as the incident beam direction, we are still able to get a maximum of intensity. So, this is what you should remember as a Bragg law. Now, you can find out what will be second order, first order, all those things you can find out only from this. Then in this condition, when delta k equals G, okay, that G can be written as small g, and some places you will find that G is written as a capital G, okay, that does not matter. Okay. This is actually is the condition for diffraction. What does this G correspond to? This G is nothing but 1 by D, correct? What is delta k? Delta k is this vector, correct? This angle is nothing but 2 theta, right? And if you take this one, this delta k will turn out to be, if this angle is theta, okay, two k sin theta will be equal to delta k, right? Is it not? So, 2k sin theta equals G. This is 2 by lambda sin theta equals 1 by D, and this is what the Bragg's law is. Okay. So, this is the condition for a Bragg condition is. So, in vector space, this is the way only which has to be written. When the between the incident beam direction and the scattered beam direction, okay, the difference between them, when it is equal to a reciprocal lattice vector, the Bragg condition is satisfied for diffraction. So, in those directions, that angle which correspond to it, you will be getting maximum in intensity will be coming. Is this clear? So, here this RMNP what you have considered as essentially like there are different lattice points are there, right? It is each lattice point we are representing it. If it is a primitive lattice, how do we represent the lattice for a primitive lattice? Primitive lattice, how do we represent? With only one point, na? The primitive lattice, only the origin we give it, because the total number of lattice points per unit cell is 1, na? So, we can represent it by the 1 by the origin if we represent it. So, that means that if this is a primitive lattice, this will represent one lattice, and this will represent another lattice, this will represent the third lattice. So, each point represents one of the unit cells, correct? So, when you take the sum of it, what we are essentially taking it is what is going to be the intensity from all the atoms put together, right? Or the amplitude which is going to be scattered from all the atoms here in this particular direction, right? That we add together, that is nothing but that condition delta k dot r equal to n is also the same, na? That what it means is that delta k for a specific value of delta k, okay, k0 is initial direction which is fixed. So, the k is fixed for a particular value of k, okay. What is going to be the amplitude which is scattered from each of the atom positions there, which adds together, that gives that intensity, okay. That will have all the information about the shape also. in this what we have to consider it is that suppose it is going to be from a very few atoms if you consider it. Okay. If the length of the sample is very small, okay, the peak will be broad. If the length of the sample is very large, the peak will be sharp. This if you relate it in a space, if you look at it, between a Fourier space, real space and the diffraction space, also the Fourier space also, this is exactly what happens. Okay, if the length is large in real space, Fourier space will have a shorter distance. If the length is small in Fourier space, length is large in Fourier space, in real space it will be short. Okay.
You mean the interatomic distance in the lattice?
No, total lattice size itself. The crystallite size. If the crystal size is very large, the peak becomes very sharp. If the crystal size is very small, the peak becomes very broad. Okay. This intensity, what we are trying to calculate, psi dash equals this factor. This is one which is a function of the real space information. Okay. And here this is we have written with respect to dV, correct? Okay. And what is this factor? This factor is essentially in a particular direction k we have calculated, psi dash, right, adding intensity. So, this is something like a function of delta k, you can take it. Okay. And the inverse Fourier transform will be that n of rho should be equal to, okay, integral of f of delta k into exponential r into d cubed delta k, right. This is how it will turn out to be.
So how do you get that?
Which one?
So from that, how you can say n of rho here?
No, I am telling. These two are related. This is one is a Fourier transform of the other. Okay, this can be derived. Okay, that part I think I will not discuss it. Maybe in a tutorial we can discuss these aspects. So from this, what you can understand or is that there is a direct link between the diffraction phenomena and the reciprocal lattice, right. And whenever delta k, the difference between the incident vector, okay, wave vector and the diffracted wave vector, that equals reciprocal lattice vector, the Bragg condition is satisfied. So, essentially what we have done today is find out a relationship between reciprocal lattice and the diffraction phenomena. We have looked at it. Now what we will do in the next class is what is the relationship between what are factors which control the intensity of the diffracted spot. We will look at it. We will stop here now.